Good morning, children. We are on to the next lecture on alkanes, and in today's lecture we will be discussing one of the chemical property, that is halogenation. I've already posted preparations of alkanes and all the general organic chemistry including nomenclature, isomerism, all kinds of effects. Okay, and so please watch those lectures also, right? So we begin with halogenation. First of all, let us see what type of reactions will alkanes undergo. Now we know alkanes have single bonds. If I consider 2 carbon atom alkane, it is having only single bonds, right? All single bonds are there. That means there are only sigma bonds present in it. There are only sigma bonds present. So one thing is that they will not be that reactive. They'll be having low reactivity because you already know that the sigma bond is comparatively a stronger bond. Pi bond will break faster, but sigma bond does not break faster. Another thing, if you check the electronegativity, carbon is 2.4 and hydrogen is 2.1. The electronegativity difference is also quite less. So we know that alkanes are non-polar also. Because they are non-polar, they are less reactive. They do not have any pi bonds. Had it been pi bond, then the pi bond breaks faster. So that is why they are less reactive. Okay, so in today's video, we will be only focusing upon halogenation, right? Alkanes mainly undergo substitution reaction. They undergo substitution reaction. Okay, because they do not have multiple bond. Had it been multiple bond, then multiple bond will change to single bond when something adds on. So those compounds which are having unsaturation, they will undergo addition reaction, and alkanes undergo substitution. And under substitution also, which category we will consider in the mechanism, right? So let us write the simplest reaction for halogenation. So suppose I consider methane, right? Methane, it can react with halogen. Suppose chlorine, it will react with chlorine. The reaction occurs in the presence of sunlight. Okay, it cannot occur in dark. It has to be always in the presence of sunlight. So when chlorine is added on, one H and one Cl will come out. So you'll have minus HCl. So the remaining thing formed will be CH3Cl. Right. So again you can have, because still hydrogen is present, so again chlorine can add on, one H and one Cl will come out. So you will have now CH2Cl2. Still hydrogen is there, so one more chlorine can add on, minus HCl. You will have now CHCl3. Still hydrogen is there, so plus one more chlorine and minus HCl, you will have CCl4. So that means one by one all hydrogens are replaced by halogen, right? This is a substitution. Substitution means it's a replacement. H is being replaced by chlorine atom. So what are the names of the products formed? The first one is methyl chloride. It is methyl chloride. The second one is methylene chloride. These are the common names I'm telling. Methylene chloride. The third one is chloroform. This is chloroform. And the last one is tetrachloride. Tetrachloride. So if we want to write their IUPAC name, this will be chloromethane, dichloromethane, trichloromethane and tetrachloromethane. So whatever alkane you take, if you take 2 carbon alkane, it will be having 6 hydrogens. One by one all hydrogens will be replaced by halogen. So this is halogenation reaction. Okay, now let us consider the mechanism of this reaction. It follows free radical substitution mechanism. Free radical substitution mechanism. And this reaction occurs in 3 steps. the first step is initiation. Chain initiation step. Initiation step we can say. Okay, it's chain initiation step, right? So now what happens in that? Let's see here. So first you took chlorine, right? Chlorine, that is the halogen. In the presence of sunlight, first homolytic fission occurs between two chlorine atoms. It was like this, one chlorine and other chlorine. Homolytic fission occurs. Homolytic fission, that means a symmetrical fission occurs. The bond is equally shared by the two chlorine atoms and it will result in the formation of chlorine free radical. Now this chlorine free radical will start the reaction. It is going to propagate the reaction. That means we can have the second step as propagation step. We can say chain propagation step. So it's a chain reaction basically, right? So it goes on till one by one all hydrogens are replaced by halogen. So it's a chain propagation step. So what happens in this now is you have methane. Now this is attacked by the chlorine free radical which is formed here. So this chlorine free radical is not stable. It will take one H from here. It will take that H from here. So actually if you see if I just draw the structure of methane like this and explain, this electron is given to hydrogen atom here. This will be again breaking. So one electron of hydrogen plus one more here, it will form what? HCl. Plus now that bond was breaking by homolytic fission. So one electron, even this carbon will get. So what you will get apart from this? You will get here methyl free radical. This is methyl free radical obtained. Now this methyl free radical is now again attacked by another chlorine. So it will be CH3 free radical. It is again attacked by another chlorine molecule. So this methyl free radical will take one chlorine from here, again homolytic fission of this chlorine. So one chlorine with one electron will combine with it. It will result in the formation of CH3Cl plus one more chlorine free radical is generated. Now this chlorine free radical again is going to attack the product which was formed here, that is CH3Cl plus one more chlorine free radical which was generated here. This chlorine is now going to take one H from here. It will take one H from here. So what it will form? It will form HCl. So when it takes H from there, it will form CH2Cl. This is the another the radical obtained. Right, the free radical obtained. This free radical, that is CH2Cl, will now again be attacked by one more chlorine molecule. So this bond again will break by homolytic fission. One Cl will go here. Every step you'll have chlorine increasing in this, and the another chlorine free radical with this H will form this thing. It will be chlorine free radical. Okay, so it will form a chlorine free radical, right? So one chlorine free radical has gone here. It has become CH2Cl2 plus one more chlorine free radical. It was not H, it is chlorine free radical. Now these two again will combine. The product CH2Cl2 will again combine with each other, and this will pull H from here. Always Cl free radical is pulling H from this side. So when it pulls H from here, you will have CH2 plus HCl, and this is now a free radical, right? Now whenever a carbon type free radical is obtained, this combines with another chlorine molecule to generate one more chlorine free radical, right? So this will take one Cl from here. It will result in the formation of CHCl3 plus one Cl is obtained. Okay, so till here I hope it is clear. Please make note of this also. I'm just pushing it upwards now, so that we can complete the steps here. So now what happens is this, whatever chlorine free radical is there will again combine with the product itself. So you will have CHCl3 plus chlorine free radical. So this will pull one H from here. It will form CCl3 plus HCl. This is a free radical. Okay, because H has gone, now valency is not complete. So this CCl3 again combines with another chlorine molecule. It now pulls and it completes carbon tetrachloride, and chlorine free radical is again obtained. Now we come to the last step, that is the chain termination step. That is the chain termination step. Now in the chain termination step, what happens is, whatever free radicals are left over, they will have equal probability to combine with each other. For example, if 2 chlorine free radicals are left over, they will combine and will form Cl2. If suppose 2 methyl free radicals are left, 2 methyls are left, they will combine and will form ethane. And if suppose you have methyl plus chlorine free radical left, it will combine and form methyl chloride, because free radicals will not be left over as such, because they are reactive. They will all combine with each other to become stable. Right? This is the complete mechanism of halogenation, which follows free radical substitution reaction. Now, very, very important thing in this is the reactivity order. Suppose you have a same alkane, and for a same alkane you have different halogens. Then the order of the reactivity is fluorine maximum, then chlorine, then bromine, and the least is iodine. Iodine is least reactive. So as per this order, it is seen that fluorine is most reactive. It is most reactive. It is in fact explosive reaction. With the fluorine, if alkane reacts, it is explosive. So that is why direct fluorination is never preferred. Direct fluorination is never preferred. In fact, it is first converted to chloride or bromide, and then fluoride can be prepared. That is indirect method, it can be prepared. We say fluorination is with the fluorine, the reaction is very fast. It is most reactive. We can say it is least selective. Least selective. Now what is the meaning of that least selective? We will take examples for this. In fact, for the last two, that is for bromine and iodine, we say they are comparatively less reactive. Among halogens, they are less reactive, and we can say they are most selective. Most selective. Most selective means they will prefer forming the stable product. Whereas here, it doesn't bother about the stability part. It reacts wherever it can comfortably react. Okay, now let's take example for this. Now let's take example here. Suppose you have this alkane. Okay, it is propane. It is having two different type of carbon atoms. This is 1 degree carbon atom. This is 2 degree carbon atom. This one is also 1 degree carbon atom. Right? Now, if these are subjected to halogenation, suppose it is reacted with bromine in the presence of sunlight, then what will be the product? Or if it is treated with fluorine in the presence of sunlight, then what will be the product? Okay, if it is with fluorine, I told you the reaction will be very fast, so even this is not required. Sunlight is also not required, it is quite fast. As I told you in the previous, page, that the order of the reactivity is, let's write the order of the reactivity. For the halogens, the order of the reactivity was fluorine, most reactive, then you have chlorine, then you have bromine, and iodine is the least reactive one. Now in that we discussed that fluorine is least selective, it is most reactive. So when it is most reactive, it will prefer forming that alkyl halide, which is very convenient, because convenient in a way when this is attacking. So this one is most protective. It is most protected because even this side there is carbon atom and on the other side. So fluorine will take one hydrogen from here and one of the other fluorine will take the place of hydrogen atom. So in a way, with the fluorine, the product will be this one. That means at one position only it will prefer. So for fluorination, what we say, the order is 1 degree, then you have 2 degree, then you have 3 degree. I mean to say, hydrogen atom which is attached to 1 degree carbon atom will prefer, be replaced by fluorine. Then 2 degree and tertiary will be least, because the steric hindrance will be there in case of tertiary. That is the case if you carry out fluorination. But if you carry out bromination, that is with bromine, then bromine is more selective. It is less reactive. More selective means it will prefer forming the stable free radical, because in the mechanism we have studied that it forms a free radical and secondary free radical is more stable. So it will prefer forming this product. That means Br will be here. This is CH3, this will be CH, this will be CH3. And the other product will be the minor product. This will be the minor product. The second product is minor product, and the major product is this one where 2 degree is replaced. Right, so for bromine, what is the order of this hydrogen atom substitution? It is 3 degree most stable, then 2 degree and then 1 degree. For fluorine, it is the reverse order. The same thing, if you can see here, this is another example I have considered. Suppose you treat this with bromine or with the fluorine, then what will happen? In this particular alkane, there are again 2 type of carbon atoms, 1 degree, 1 degree, 1 degree, and this is 3 degree. So with bromine, undoubtedly more stable one will be 3 degree. Here there was no 3 degree, so 2 degree was preferred. So it will prefer attacking 3 degree carbon atom, that is this one. So these will be remaining as such, right? And if it is, this is the major product and this will be the minor product, right? This will be the minor product. You can complete the valencies, right? So this is the major product. This is the major product and this one is the minor product for bromine. And if you are talking about fluorine, then of course it is this way. This will be the major product. Fluorine will prefer attacking the less bulky one, less hindered one. Okay, the other one will be not formed. This will be the major product, right? So 1 degree will be the major product in case it is fluorine. Clear? Then if it is chlorination, chlorination is at times more reactive and at times more selective. So if it is a combination of 1 degree and 2 degree, then in that case it is forming 2 products. This is minor, this one is major. Difference is though not much, it is 55% and this one is 45%. Okay, and if it is 3 degree present, then it will prefer forming more reactive product. That means it will prefer forming this one rather than more selective one. Okay, so this will be the major product and this will be the minor product. Because for chlorine, it can be both. It can be at times more reactive or selective depending upon what is the alkane you have considered. Fine? Okay, now let's talk about iodination. It's an important question asked. At times even the recent question is asked based upon iodination. It says, when you carry out iodination, we first discussed that it is reactivity is less. Okay, it will form this I plus HI. The question is, when iodination is done, it is generally carried out in the presence of strong oxidizing agent. that is HNO3 or HiO3. The reaction is generally carried out in the presence of these oxidizing agents. Why? Why? Iodination is carried out in the presence of strong oxidizing agents, that is nitric acid or iodic acid. So answer to that is iodination is reversible reaction. It is reversible because it's slow reaction. It is reversible. So what is done? We use oxidizing agent. So what that oxidizing agent will do? Suppose I consider HiO3. So this HiO3 will react with one of the product. Say Hi. It will react with the product and it will generate I2. That means reactant. And water will be formed. If you balance it, this will be 3. This will be 3 and this will be 5. Okay, I'll just repeat. We say it is iodination is always carried out in the presence of oxidizing agent because iodination is reversible. So that oxidizing agent will react with one of the product. It will react means its concentration will decrease. When the concentration of the product is decreasing and this I2 is formed, that means the concentration of the reactant is increasing. So equilibrium will shift in the forward direction. The equilibrium will shift in the forward. So as per Le-Chatelier's principle, if you remove the product and increase the concentration of the reactant, equilibrium will shift in the forward direction. Suppose if you use HNO3, then what happens? HNO3 will combine with Hi and it results in the formation of water plus NO2 plus I2. You can balance this 2, 2 and 2. So either of the two oxidizing agent can be used for this particular reaction. Right? So iodination is never done otherwise. It is always done in the presence of good oxidizing agent because it is reversible and the oxidizing agent will remove the product and increase the concentration of the reactant. Hence, as per Le-Chatelier's principle, equilibrium will shift in the forward direction. That's all for today's lecture. Okay, so learn whatever we have done in today's class. Thank you.